Hey everyone, I'm Austin Anderson and this is lab number 12 for Chem 1314, Molecular Architecture. So this experiment is designed to help you visualize molecules and why they have the shapes that they do. So before you can start trying to figure out the shape of a molecule, the first thing you need to do is figure out the number of valence electrons for each atom in that molecule. Okay, so for today's experiment, we're going to make it a little bit easier on us. We're only going to be dealing with elements that do not have variable oxidation states. So we're not dealing with any of the transition metals. Okay, so we're just dealing with group 1 and 2A elements and then group 3A through 7A elements. So how do you find the number of valence electrons? All right, well, it's pretty simple here because all you have to look at is the group number that it's in. Assuming you don't have an ion, so assuming you don't have a positive or negative charge, then the number of valence electrons is going to be equal to this group number. So hydrogen, everything underneath it, is group 1A. It has 1 valence electron. Nitrogen, everything underneath it, is group 5A. Those elements have 5 valence electrons. Now say you had like a calcium 2 plus in your molecule, okay? That, you can still rely on the group number it's in, but you know if it's 2 plus, then you're going to have to subtract 2 electrons from it to get the correct number of valence electrons. All right, so once you know the number of valence electrons, you can start working on a Lewis structure. All right, so you have to figure out what the central atom is. Now, generally, the central atom in your molecule is going to be the most electropositive atom. Your more electronegative atoms are going to go on the outside. They're going to be your surrounding atoms. There is an exception, however. If you have hydrogens in your molecule, those are always going to be part of the external atom group. Okay, hydrogen atoms can only ever form one bond, so that means they can't be a central atom. So once you figured out the central atoms, you draw your other atoms around it, and you start filling in your valence electrons. So this is drawing the Lewis dot structure. All right, so let's take a water molecule, for example, here and making a Lewis structure. Okay, so once again, like I said, oxygen is the most electronegative element here, but it has to go in the center because hydrogen can only ever form one bond. So to do your Lewis dot structure, the first thing you do is start adding your valence electrons. All right, so your hydrogens each have 1 valence electron. Your oxygen has 6 electrons. Whenever you fill in your Lewis dot structure for this central atom, you draw 1 electron in each group first. Okay, so you don't make any pairs to start out with. You fill it in. Now you have 2 electrons left. Those form pairs. Okay, so those are going to be your lone pairs in the oxygen. So now you can actually go in and draw your covalent bonds. You're making a pair of electrons out of 2 single electrons. So that's what's going to happen right here. So there you have your water molecule. Now we'll get into the actual structure and 3D shape of this molecule here in just a little bit. So VSEPR theory, VSEPR, stands for valence shell electron pair repulsion theory. So VSEPR theory is based off of the fact that like charges repel each other. Now in VSEPR theory, you have lone pairs and bonding pairs. Okay, so lone pairs, those are just your pairs, your lone pairs of electrons that aren't involved in bonding. Bonding pairs are, as the name describes, are bonding pairs of electrons. They're a pair of electrons that form a covalent bond. All right. Now, your types of covalent bonds can be sigma bonds and pi bonds. I'll get into sigma versus pi bonds a little bit later. So single, double, and triple bonds, they're counted as one bonding pair, okay? It's counted as one electron dense region is a better way to describe this, okay? And then single non-bonding electrons are counted as a lone pair. Getting into it, you have, for example, you have a molecule that has 2 electron dense regions, all right? So If there's no lone pairs, then you have a linear molecule. Even if there was one lone pair, you'd still have a linear molecule. So if basically, if you only have two atoms in your molecule, the only thing it can be is linear. Okay. Now we get into a little bit more complex. We get trigonal planar tetrahedral. So due to this electron pair repulsion, your atoms in the molecule are going to space each other as far apart as possible. And that's going to be due to the bonding pair of electrons that are shared between the atoms. So the electrons in each of these regions, they're trying to be as far apart from each other as possible. So in a linear molecule, as far apart they can get is 180 degrees. But whenever you have three regions, the furthest apart you can get is 120 degrees. For four regions, the farthest apart you can get is 109.5. For five regions here, which is trigonal bipyramidal, we don't have to worry about this today. You have two different bond angles. You've got something similar to trigonal planar, which around the equatorial axis of this molecule, your bond angles are 120 degrees. But through the equatorial axis, so straight down through here, your bond angle between, say, this pair and this pair, that's 180 degrees. But this pair and one of these equatorial pairs, that is only 90 degrees. Now, octahedral here, the maximum bond angle you can possibly have is 90 degrees. So that's how these molecules are going to arrange themselves. So once again, it's just how far apart can you spread out these charges to help stabilize the molecule. Now, let's talk about lone pairs and how they actually affect the molecular shape. So we'll start off with tetrahedral. All right, tetrahedral, you have bond angles 109.5. Now, if we take away one of these atoms but leave the pair of electrons, that's now a lone pair on the central atom. This lone pair is still going to be repelling everything else. It's still going to be repelling all of the bonding pairs. So your electronic geometry is still going to be tetrahedral. However, your molecular geometry, you can't see that lone pair of electrons. All you can see is the fact that your molecule now looks trigonal pyramidal. You get to bent, you have two lone pairs. Your electron pair geometry is still tetrahedral. Those pairs of electrons, be it lone pairs or bonding pairs, they're still roughly 109 degrees apart from each other. All right. So for today's lab, like I said, we don't have to worry about trigonal bipyramidal and octahedral, but you can see here in the structures how the molecules start to take their shapes depending on the number of lone pairs. So if you replace one of these outer elements or outer atoms with a lone pair in a trigonal bipyramidal, the electron pair geometry stays the same, but the molecule itself looks like a sawhorse or seesaw now, because you can't see this pair of electrons. All you can see is the effect it has on the shape of the molecule. Same thing with T-shaped. You replace two bonding atoms with lone pairs. Now you have T-shaped. And you replace a third atom with a lone pair, you now get a linear molecule. One thing before I get into the molecules that we're actually looking at today is I need to talk about polarity. So polarity is strictly based off of electronegativity difference in the molecule. So I'll show your polarity with the following two molecules. Your first one is Cl2, okay? So you've got two chlorine atoms. They're going to have the exact same electronegativity value, so you have a completely nonpolar molecule here, all right? When you draw this, or when you make your Lewis structure, you have three lone pairs around each chlorine and one bonding pair that they share. So the total number of lone pairs in this one would be 6, and your bonding pairs is 1. Now, this, whenever you have a single bond, that is always a sigma bond, okay? Whenever you have a double bond or a triple bond, one of the bonds counts as a single bond, the other bonds count as pi bonds. So looking at the 3D structure of this molecule, you have a completely linear molecule. Whenever you look at it straight down the axis, you can't see the other element. You can't see the other atom in the molecule. But whenever you rotate it, you can see both. So here's your 3D structure of Cl2. So the next molecule we're going to look at is hydrochloric acid, HCl. So you have a chlorine bound to a hydrogen. Now chlorine is pretty electronegative, hydrogen not so much. So this is a polar molecule. So because of the electronegativity difference here, you have what's called a dipole moment. All right, so basically what a dipole moment is, it's telling you have a positive end of a molecule and a negative end of the molecule. The negative end of the molecule is where more electrons are going to tend to be gathered. So the more electrons are going to be gathered around or gathered closer to the most electronegative side of the molecule. So in this case, that's our chlorine. You've got a large surplus of electrons on the chlorine side and a deficiency of electrons on the hydrogen side. So you have a net dipole that points in the direction of the chlorine in this case. So what this molecule looks like in 3D is this. Once again, totally linear, but you can see the polarity difference based off of the size of our two spheres here. So once again, the total number of valence electrons here, you would have 7 for chlorine, 1 for hydrogen, so total valence electrons is 8. You have 3 lone pairs, 1 bonding pair, and you have 1 sigma bond. Now, our next molecule, carbon tetrachloride. You have your most electronegative element in the center, that's carbon, surrounded by 4 chlorines. Each chlorine has a valence shell full of 7 electrons. Carbon has 4, so if I would have drawn my Lewis dot structure, I would have put 4 dots around carbon and then 7 dots around each chlorine. I connect my dots and I have my 4 covalent bonds around carbon. So this molecule's 3D structure, since you have 4 electron regions, you have to space those as far apart as you possibly can. That's going to be 109 degrees between each pair. So you have a tetrahedral structure. The tetrahedral structure allows the electron pairs to be as far apart as they possibly can. So our next structure here is trichloromethane, better known as chloroform, CHCl3. It's pretty similar to carbon tetrachloride. However, one of the chlorines has been replaced with a hydrogen now. Because of that, we now have a polarity difference. In the previous one, these are technically you do have polar bonds here, but because everything is spaced out evenly and all the bonds are exactly the same, you don't have a net dipole, so you have a totally non-polar molecule. But the moment you change one of those outer atoms to something that has a different electronegativity value, you get a polar molecule. So now, because I have replaced one of the chlorines with a hydrogen, I do have a dipole moment. So my dipole moment now has a positive end over here where the hydrogen is and a negative end between the 3 chlorines. This molecule would have 3 lone pairs around each chlorine, so it's a total of 9 lone pairs and 4 bonding pairs. You have 4 sigma bonds, no pi bonds because you don't have any double or triple bonds. So here we see the Lewis structure for our next compound, hydrogen cyanate. So this structure, you can see we do have some double bonds in it. And that is going to alter the shape of our molecule significantly. So let's break this down a little bit. So around the oxygen atom, you have 3 regions of electrons. You have 2 lone pairs and then one bonding region. Okay, so the electronic geometry around that oxygen is trigonal planar. Around your carbon atom, you only have two electron regions, so around the carbon, you have linear electronic geometry. Around the nitrogen, you have two bonding regions, one lone pair. So you have trigonal planar electronic geometry, but the molecular geometry around this is bent. So let's just go ahead and bring up the 3D structure of this. You can see that through the nitrogen, carbon, and oxygen, it's totally linear. You can see your double bonds between the nitrogen carbon and oxygen carbon. And you see this hydrogen hanging off at an angle. The reason why the hydrogen is bent at an angle and not in line with everything else is because of this lone pair of electrons. This lone pair is pushing the bonding pairs away from itself, causing the molecule to become bent around this nitrogen atom. So here we have our next molecule, hydrogen sulfide, which is very similar to water, H2O. So you have your central sulfur surrounded by two hydrogen atoms. You have a bent molecule here because there are 4 electron regions and 2 lone pairs. Your electronic geometry of this molecule is still going to be tetrahedral because you have 4 electron regions around this central atom. However, your 3D structure of the atom is going to just look bent because you can't see those lone pairs. So technically you have a lone pair sticking off here, a lone pair sticking off here, but you can't see them. So all you see is the bent molecule. So our next molecule is formaldehyde, HCHO. So in this little structure, once again, you see you have a double bond in it. All right, so you've got 1, 2, 3 sigma bonds, and then you add 1 pi bond for each double bond. So you've got a total of 3 sigma bonds and 1 pi bond. Your total valence electrons here, you've got 2, 4, 6, 8, 10, 12. On this molecule you have 2 lone pairs, and even though technically you have 4 bonds, you only have 3 bonding pairs according to VSEPR theory. So being as you have 3 bonding pairs, your 3D structure of this molecule looks something like this. You have a trigonal planar molecule. All right, so now we get into a little bit more complex molecule here with hydrazine. Hydrazine, you can consider either one of the 2 nitrogens as your central atom. So whenever you're looking at the electronic geometry and the molecular geometry around the central atom here, you can ignore the hydrogens coming off of the other atom. So try to envision it without the hydrogens on here. So just looking at this nitrogen, for example, you've got 3 bonding pairs, 1 lone pair. So that means your electronic geometry is tetrahedral, and your molecular geometry around this nitrogen is trigonal pyramidal. All right, so bringing up the 3D structure, you can actually see this. So if you're able to picture this 3D structure without these 2 hydrogens hanging off of the other nitrogen, you see that it is trigonal pyramidal. Okay, and our next molecule, which is the chlorine difluoride ion, has a positive charge. Okay, the positive charge is always going to be placed on the least, well, 9 times out of 10, the positive charge in an ion is going to be placed on the least electronegative element. Okay, so in this case, that would be chlorine. So you have your chlorine as your central atom, and you have your fluorines on the outside. You have 2 bonding pairs around the chlorine, and the chlorine has 2 lone pairs. So this is going to be very similar to water in the molecular shape. So it's going to be tetrahedral electronic geometry. However, the molecular geometry is going to be bent. The next molecule is carbonyl sulfide. Once again, you have to start including some double bonds in here. So you have a double bond between your carbon and oxygen, double bond between your carbon and sulfur. So your oxygen has 2 lone pairs, 2 bonding pairs. Sulfur has 2 lone pairs, 2 bonding pairs. But our central atom, carbon, you have 2 electron regions total. So your molecular shape is linear here. The next molecule, the chloride ion, it's just like chlorine difluoride, and it's just like water. It's tetrahedral electronic geometry around the chlorine and bent molecular geometry due to the lone pairs coming off the chlorine. Now here you have a lot of formal charges. The more formal charges you have on a molecule, the less stable that molecule tends to be. So the chloride ion is going to be fairly unstable. That's because you have formal charges on every single element. None of the elements are totally happy. So everything here may be happy in the fact that it follows the octet rule. However, your oxygens and chlorines are going to be unhappy because they have the formal charges on them. Oxygen has too many electrons, chlorine has too few electrons around it. The next molecule we've got is hydronium. Hydronium ion is similar to water, but the oxygen now has a extra proton or an extra hydrogen hanging off of it. Okay, so one of the lone pairs on the oxygen has now bound to a free hydrogen atom. So here we can see the molecule has 4 electron regions with 1 lone pair. So we have tetrahedral electronic geometry, but our molecular geometry is now going to be trigonal pyramidal, as you can see here. Lastly, before I end the lab today, I want to go ahead and go over the difference between sigma bonds and pi bonds when looking at Lewis structures. Okay, so every single bond you have has at least 1 sigma bond. Okay, double bonds and triple bonds have 1 sigma bond and multiple pi bonds. So for a double bond, you have 1 sigma bond and 1 pi bond. For a triple bond, you have 1 sigma bond and the other 2 are pi bonds. Okay, all right, that pretty much sums up everything I want to say for this lab. Thanks for listening in. I'll see you next time.